Last up, we have our final section on probability. It's section 8.5 on random variable, probability distribution, and expected value. They're all very closely related to each other. They all lead into this concept of expected value, which is essentially the average value of the outcome of an experiment. So I think we'll explain this as we go through with an actual experiment. So behind me I've got the experiment we're looking at is tossing 3 fair coins. It's an experiment we've looked at several times already. So our sample space is, of course, all the different possible outcomes. So for example, the first coin might be a head, second coin is a head, third coin is a head, so HHH. Or we might have first coin is a head, second coin is a head, third coin is a tail, and so on. We've got 8 different possible permutations there, 8 different possible outcomes. And instead of looking at the actual outcomes themselves, I'm interested in just measuring per outcome, how many heads do I have per outcome? All right, so we're interested in measuring the number of heads in each outcome. So here I've got a table behind me where I've already done this. I've measured the number of heads for each simple event in the sample space. I've counted the number of heads. For example, HHH is 3 heads, HHT is 2 heads. Down here at the bottom, TTT is 0 heads, and so on. And here's where I'm going to get a little bit formal with this. Of course, this is a simple idea, but what I'm really doing is I have a function. I have a function that for every single simple event, it's assigning a number to it, right? So for example, HHH gets the number 3 assigned to it. It's the number of heads in HHH. HHT gets the number 2 assigned to it. So I've got a function that takes the elements in the sample space and it maps them to a number. And so to each outcome, we have assigned a number. And that number, I'm going to be very formal because I'm thinking this is a function. I'm going to call this x, capital X usually, of e sub I. So e sub I is just an event in here, and x is the function. So you plug in the event, and you output x of e sub I, which is this number. And so the point is that this is an example of what's called a random variable. Right, so number of heads, this is what I'm calling x of e sub I, and it's a function. It's a function where I plug in the simple events and I output a number. And the number, in this case, that I'm assigning to it is the number of heads in that particular outcome. It's an example of a random variable. Anytime someone first learns about random variables, the person sort of explaining it to them points out that this is a terrible name. This absolutely should not be called random variable, but it's a name that's stuck over the centuries. Why? Well, because it's neither random. I'm not making a random assignment here or anything. I'm making a specific choice. And 2, it's not a variable, it's a function. Right, but the name is what it is. So let me formally define this. Definition, a random variable is a function that assigns a numerical value. It's a function that assigns a numerical value to each simple event in the sample space. To each simple event in the sample space. So random variables are actual functions. And what I'm saying there is, for example, for this random variable x of HHH, I plug in my event HHH, and I output the number 3. So it assigns to this outcome HHH, it assigns to the number 3. So formally this is what's happening in the background. It's pretty obvious, pretty easy to count the number of heads, but formally what I'm doing is I have a function that assigns a value to each outcome. Alright, next up, what do I want to do? So now I've got this random variable that assigns to each outcome the number of heads in the outcome. Next up, I want to assign a probability to each of these occurrences in the range of this random variable. Right? So I want to assign a probability to the the outcome of 3. What's the probability of getting 3 heads? I want to assign a probability to 2. What's the probability of getting 2 heads? Probability to 1, what's the probability of getting 1 head, and 0, right? So this is what I have over here. I have a table that's going to do this for us, or keep track of this information for us at least. So number of heads, 0. What's the probability of getting 0 heads? Well, there's only one way to get 0 heads, is TTT. So one outcome out of 8 in the whole sample space. So the probability of getting 0 heads is 1/8. What about 1? Well, there's 3 outcomes with 1 head in them out of 8 possibilities in the sample space, so probability of getting 1 head is 3/8. 2, you can check this, probability of getting 2 heads, also 3/8. There's only 3 ways to do that, and there's exactly 1 way to get 1 head. So probability of getting, 3 heads, sorry. The probability of getting 3 heads is 1/8. Okay, so for each sort of each value in the range of this random variable, I've now assigned a probability. This has a name as well. This probability function p of x is called the probability distribution. So p of x is called the probability distribution of the random variable. Of the random variable x. So formally that's what it's called. It's a probability function that assigns a probability to each of these image values of the random variable. And so far, we've really done nothing that we haven't done before. We've assigned some formal names to these processes, but all I've really done is I've looked at the probability of certain compound events, right? The compound event of rolling or tossing 0 heads, or 1 head, or 2 heads, or 3 heads, and we've looked at the probability of these compound events. So far, nothing new here, just some new formal terminology, but in comes the new part, which is expected value. All right, so let's look at what this actually says. All right, so this table says that on a given toss, right, a given toss of all three coins, you would expect to see 0 heads 1/8 of the time, right? So this says that we would expect to toss 0 heads 1/8 of the time. How many times would we toss 1 head? 3/8 of the time. Toss 1 head 3/8 of the time. Two heads, also 3/8 of the time. And 3 heads, 1/8 of the time. So what I'm interested in is, in the long run, what's the average number of heads that I'm going to see? Right, across all of the different outcomes, what's the average number of heads? So in the long run, the average number of heads per toss of the 3 coins is, well, how would I compute this? Well, I'd probably want to weight the number of heads that I see by its probability, right? And then just add them all together. So, for example, I've got 0 heads, well, that occurs 1/8 of the time. So I'm just going to weight the outcome of 0 heads by its probability. Plus I've got 1 head, well, that occurs 3/8 of the time, so I'll weight 1 head by 3/8. I've got 2 heads, that occurs 3/8 of the time, so I add a plus 2 times 3/8, and I'm sort of running out of space here, so I don't really want to erase my table, but I'll leave some of it there. And plus 3 heads, we know that occurs 1/8 of the time. Alright, so this looks like this expression, if I just weight the outcomes by its probability and add them all together, that should give me the average outcome. And what is this? If I add them all together, I've got 0, 3/8 plus 6/8 plus 3/8. That is 12/8, or 1.5. Does that sound reasonable to you? Well, it should, right? Of course, I can never actually toss and get 1.5 heads, but on average, that's how many you would expect to see. Right? You would expect sort of on average to see exactly half of the coins being heads. And because I've got 3 coins, well, half of the coins being heads would be 1.5 of them, 1.5. So this has a name. This is called the expected value of this random variable. And what I'm going to do is call this E of X. It's the expected value. The expected value of the random variable X. And the way expected value is computed is you just take all of the values in the range of X, you weight them, so you multiply by the probability of those outcomes, and you just add them all together. Alright, so this is the sum of each image of X weighted or multiplied by, weighted by its probability. And that probability is given by your probability distribution function. So this is a very long explanation of everything that goes into these problems. You'll see as we do many examples here that it's really not that bad. And I guess we'll just jump straight into them. So we'll do another example. Alright, so expected value often pops up when talking about games. So here's a very simple game. You draw and keep. It's a wonky looking K. My handwriting's not the best anyway, but you draw and keep a single coin from a bowl that contains 120 nickels and 80 quarters. So what's the expected value of the game to you? In other words, after you play this game, how much money would you expect to have on average? So at best you draw a quarter, at worst you draw a nickel, but on average you'd fall somewhere between those two values, right? So on average, what's the expected value? What's the average amount of money you'll leave this game with? So let's see, I have to assign a random variable. So it'll be X, and what do I want to do? So what am I going to assign to these outcomes? Well, there's only 2 different outcomes, right? Either I choose a nickel or I choose a quarter. I have to assign values to these things, so if I choose a nickel, how about I assign that the value of 5 cents, 0.05. Right, so this is 0.05 if a nickel is drawn. So if the event is drawing a nickel, or I draw a quarter, in which case my outcome will be 0.25 if a quarter is drawn. And so there's my random variable. To every single outcome I've now assigned a value. Nickels give me 5 cents, or $0.05, and quarters I'm assigning the value 0.25. So now I need a probability distribution. So here's my images of the random variable. I'm just going to call these x sub I from now on. Typically what the textbook does as well. So I'll just call that x sub I. And we've got 0.05 and 0.25. And we need a probability for each of these. Well, what's the probability of getting 0.05? What's the probability of drawing a nickel? What would that be? That would be 120 over 200 possible coins. So 120 over 200. 120 over 200 is, as a decimal, that's 0.6. And the probability of drawing a quarter would be 80 over 200 possible different coins we can draw. 80 over 200 is 0.4. You'll notice, by the way, my probability distribution, when you add them all together, it's always got to equal 1. You can check that on the last example too. And these probabilities are always somewhere between 0 and 1. So sure enough, these add up to 1. We're doing good. And the last thing we need is now we just need the expected value. How do we find expected value? Well, it's a very simple process. You just take your outcomes, so 0.05, and weight them by their corresponding probability. So 0.05 times 0.6. And then you add them together for all the different possible images in the random variable. You weight them all by their corresponding probability, and you add them all together. So 0.05 times 0.6 plus 0.25 times 0.4. And plug this into a calculator. I got, you don't really need a calculator, but I got 0.13. And I want to put some units on this. Of course, we're talking about dollars here, right? So this is the expected value of this game. You play this game, you're expecting on average to walk away with 13 cents. You should always check, is my answer reasonable? Well, certainly I'd expect to walk away with something between 5 cents and 25 cents. And so yeah, this is a reasonable answer. So hopefully you're getting the impression that calculating expected values is not a difficult process. It's just this part right here. You just have to build your random variable, which you'll get better as you do more of these, and then the corresponding probabilities of each of these outcomes. So we'll do another example. Once again, another game question, because game or expected values is a really common concept in the concept of games, or in the context of games, I should say. And once again, we'll come back to flipping coins. So 2 coins are flipped. You win $2 if either 2 heads or 2 tails turn up, and you lose $3 if a head and tail turn up. What's the expected value of this game? Well, intuitively, this is a very bad game to play, right? Because 2 heads and 2 tails is exactly half of the possible outcomes, and a head and a tail is the other half of the possible outcomes. So half of the time you're going to win $2, and half of the time you're going to lose $3. So on average you're losing money. I'm expecting the expected value to be negative. So it's a terrible game to play, but all we're going to do now is we're going to go ahead and formalize that thought process. So once again, my random variable x of e sub I is what? I want to assign values to all of the possible outcomes. So what are my outcomes? I either have HH, I've got HT, I've got TH, or I've got TT. And I want to assign a numerical value to each of these outcomes. Well, what numerical value would make sense to assign to them? It's the amount of money I'm going to win or lose, right? So HH is a winner. I win $2. HT is a loser. I lose $3, so I'll assign to that the value minus 3. TH is also a loser. I lose minus $3. Or maybe I should say I lose $3 instead of having a double negative there. And TH is I win $2. So these two values get, or these two outcomes get assigned the value 2, these two values get assigned the value -3. That's a random variable. Alright, so we've got 2 and -3. What's the probability that I want to assign to each of these values? Well, 2 happens exactly half of the time, so 1/2. And -3 happens, again, 2 out of 4, or exactly 1/2 of the time. So each of them I'll assign the equal probability 1/2, or 0.5. And to compute the expected value now, I've got 2 times 1/2 plus -3 times 1/2. So this is 1 minus 1.5, or minus 0.5, and I'll put some units in there, dollars. So the expected value of this game is, as we expected, it's negative, and it's negative $0.5. In other words, on average, every single time you play this game, every single time you flip these coins, you're expecting to lose 50 cents. So it's not a good game to play. I'll make a note. So a game is called fair if its expected value is 0. If its expected value is 0. So this is not a fair game. So you might see some problems in the homework about fair games. Fair means its expected value 0. Sometimes they'll ask questions like how should you modify this game to make it be fair? Well, I would need to modify these payout schemes so that this equals 0 at the end of the day. So either make it you win $3 and then lose $3 to make it fair, or you win $2 and only lose $2. Either one would modify this game to make it be fair. Alright, so I just want to do a couple more examples. I had a much more tricky example than the 2 or 3 we've done so far. Playing another game here, a 5-card hand is dealt from a standard 52-card deck. If the hand contains at least one king, you win $10. Otherwise, you lose $1. What is the expected value of this game? So if you're drawn a hand that has a king, one or more kings, you win $10, otherwise you lose $1. What's the expected value of this game? Well, this comes into the probability of being dealt at least one king. Okay, so we're going to have to compute that, obviously. So let's see. What am I going to do? Let's just jump straight to our table here with our random variable and our probability distribution. What random variables how do I want to assign this random variable, or construct this random variable? Well, to every single card, every single hand that I have, every single possible outcome, I want to assign to it either plus $10 or minus $1. Alright, so I've only got two outcomes. Either I win $10 or I lose $1. What are the probabilities of each of these? Well, for example, if I want the probability for minus 1, what would this be? This would be the probability of 0 kings. And notice that I'm going with the probability of 0 kings first, because the probability of at least one king is much harder to compute. In fact, the way I would want to find the probability of at least one king is do 1 minus the probability of 0 kings. Right? Remember, that's how we compute probabilities of complements. So we've got the probability of 0 kings. What's this going to be? Well, how many ways can I have 0 kings? Well, if I remove all 4 of the kings from the deck, then I'm choosing 5 cards from 48 remaining cards, right? So this is 48, choose 5. Remember, if I take away all of the kings, there's 4 of them from a 52 card deck, I have 48 cards. How many combinations of 5 cards can I form from 48 cards? Well, it's 48, choose 5. Over the number of elements in the sample space, which is all possible 5-card hands, so that's 52. Choose 5. So there's the probability of 0 kings. This is why this is a much harder problem, is because computing this probability is more difficult than the simple ones we did before. But yeah, probability of 0 kings is number of ways to draw 0 kings, 48 choose 5, over total number of possible hands, 52 choose 5. I plugged this into a calculator. I got, after rounding to 2 decimal places, I got 0.66. Okay, so the probability we want to assign to the value 10 would be the probability of at least 1 king. Probability of at least 1 king and this is just 1 minus 0.66. And the probability of at least 1 king should be 1 minus the probability of no kings. And that is 0.34. So we'll put these up here in our little table, 0.34 and 0.66. And the last thing we want to do is now compute the expected value of the game. And so the expected value of the game is 10 times 0.34 plus minus 1 times 0.66. Which, plug this into a calculator, I got $2.74. Actually, not that hard to compute it mentally. 10 times, this would be $3.40 minus 66 cents is $2.74. So this is a great game to play, right? Every single time you play this game, your average profit is $2.74. You're going to lose sometimes you're going to win $10, and the point is that this payout of $10 is so high that on average you're making money. So if you ever walked into a casino and you saw someone offering this game, you would play this all day, because on average you're going to make a lot of money every single time you play. Of course, you'd never see this game in a casino because all of their games are set up to make sure that they make money. But I digress. We'll do one more example. And we'll get away from games. We'll do an insurance example. All right, last example we'll do. It's an insurance question. So here's just an example. An insurance company charges an annual premium of $75 for $200,000 in coverage. So a $200,000 insurance policy against a house burning down. So if the probability of a house burning down in a given year is 0.0003, of course this is an empirical probability, there's no theoretical probabilities here, this would just be sort of measured over time in the real world. If the empirical probability of a house burning down in a given year is 0.0003, what is the expected value of the policy to the insurance company? All right, so how are we going to do this? Well, we're going to set up our table, as we always do, with our probability distribution. And what's my random variable going to be? Well, there's really 2 outcomes in this experiment. Either a house burns down or it doesn't. So if a house burns down, in the event that a house burns down, we should assign the value negative $200,000, because that's how much this insurance company is going to lose if a house burns down. They have to pay out $200,000. And the probability of this occurring is just a very small 0.003. The other possible outcome is the house doesn't burn down. What value should we assign to that? Well, in that case, if the house doesn't burn down, the insurance company makes $75. So in the event it doesn't burn down, we've got our random variable assigns the value $75. And when would this happen? Well, this would happen all the rest of the time, so this would be 0.9997 is our probability of not burning down. It's just 1 minus 0.0003. So now all we have to do is compute the expected value. The expected value is each of these values times their respective probability. It would be minus 200,000 times 0.003 plus 75 times 0.9997. Barely enough room to get on the board there. So simplifying this, I plug this into a calculator. I got $14.98. Which makes sense. If the expected value is negative, this insurance company would be losing money and they'd need to readjust their pricing here. So obviously they want a positive expected value per insurance policy. And it's a close to $15, so a small profit per insurance policy. Small enough that someone else would probably be willing to pay this, because even though on average people buying insurance policies are losing money, you do it because you're willing to part with this very small amount of money in order to avoid having to pay in a catastrophe this huge amount of money that you might not have on hand, $200,000. So you pay this small fee, $15, to avoid any sort of catastrophes like that. In any case, yeah, so this is a pretty good example. I like this. This sort of explains the expected value, the average outcome per insurance policy for these companies. So anyway, this is expected value in a nutshell. The hard part is building this table, right? Choosing your random variable and assigning the probabilities to them. But once you have it built, the way you compute expected value is you just multiply each of these values in the range of your random variable times their corresponding probabilities and add them all together. We'll stop here. Thanks.